The circuit here is the one that was left on the board the end of last class. And in this video we're going to solve where it sits now, or where the Q point is. The Q point is really, if you imagine a load line between saturation and cutoff, the Q point is where we're trying to center that load line. If you were to measure voltage from the collector to the emitter, if this voltage was 0, it's a piece of wire, we call it saturation. If this voltage was close to VCC, it would be open, or an open switch, and that would be what we would call cutoff. So what we got to figure out is, where is it between those two? And what we're going to do is we're going to run through how to find all these here now. The first one, probably the easiest one to find, is if you imagine this VBB, or this 6-volt supply, as powering this loop here. Right? Remember, everything comes out the emitter. So there's sort of two paths in. There's a base and a collector that come into the transistor, and everything's coming out the emitter. So if you imagine this loop has a 6-volt supply available to it, and VBE, remember, for conduction, we talked about this in a previous video, to be in that active region, this would be forward biased. A forward biased PN junction is 0.7 of a volt. Knowing that's 0.7 of a volt, looking at this loop, we can make the statement that VRB is equal to VBB, right? So that's this supply voltage here, minus that 0.7. So in other words, 0.7 is lost on the base emitter junction. The remainder is going to be on the base resistor. So VBB minus VBE. We said that the solution for that then would be 6 volts minus 0.7 volts, which equals 5.3 volts. That's pretty straightforward, I think. Ohm's law then, the one we're really after, would be IB. So what's the current on the base? The current on the base is going to be just Ohm's law, right? VRB divided by RB, which is going to give us 5.3 volts, divided by 15 kilo ohms, which is 353.3 microamps. I'll put that over here because we're going to run out of space, I got a feeling. 353.3 microamps. Okay, so now we have a base. If you remember from theory class, beta is how much bigger the collector is than the base. In other words, that's how much does it amplify. So if it's sitting here, whatever the base current is, the collector will be beta times larger. Well, if we know the base and we know beta, then we could say the collector current is going to be beta times bigger than the base current. And that's simple enough. We'd say then 200 times 353.3 microamps, and that gives us, I think it's 70.67 milliamps. So there's the collector current, right? Beta times larger than the base. 70.67 milliamps. So there, we have these two. If you imagine that the transistor is in essence a device with two currents, there's a base current and a collector current, and the sum of those two, there's two ways in, only one way out, that's on the emitter. So the emitter ends up being the sum of the base plus the collector. The base was 353.3 microamps, and the collector was 70.67 milliamps. So the emitter current, or what's flowing on the emitter, is going to be the sum of the two, which is 71.01 milliamps. Right, so here we've got 71.01 milliamps flowing. So what we've got here is we've solved now for all of the currents in this loop. Now we have to deal with this larger current and voltage loop. Again, remember there's two ways in: currents flowing in the base or flowing in the collector, all currents coming out the emitter. So in this loop, what we'd really like to be able to find next would be VCE. VCE, if we know there's 12 volts in the loop, right, there's a 12 volt supply, and that 12 volts has to be divided between RC and the transistor, then what we can say is VCE, the voltage collector to emitter, is going to have to be equal to the total voltage available minus whatever's on the resistor. Well, we don't know what the resistor voltage is, but we know what size the resistor is, and we know how much current's flowing. Those combined give us the voltage drop. So we could say 12 volts minus 120 ohm resistor, and IC was 70.67 milliamps. And that tells us then that VCE, I guess I could write it all out, will be 12 minus 8.48 volts, which gives us a VCE of 3.52 volts. So 3.52 volts. So you can see it's not a very centered Q looking at this, right? Because if you remember, if it was saturation, I would have expected a VCE in saturation of somewhere near 0. And in cutoff, I would have expected a VCE somewhere near 12. So a centered Q, right, the center of the Q, if it was working right, should have been around 6. But it's not 6. It came in at 3.52, meaning that it's a little bit closer to saturation than cutoff right now. So the only thing left to solve for is this VCB, and that's pretty straightforward. I mean, all the numbers are there now. We want VCB. So if you imagine down here is ground, and this is where we're referencing. If I were to measure from here, right, to the base, I'd read 0.7. If I were to measure from here to the collector, right, I'd read 3.52. So it's pretty straightforward then, that all we have to do is take B, voltage at the base. Actually, no, it should be VC minus VB. And we have these numbers, right? VC, measuring from ground, was 3.52 volts minus 0.7 volts, right? So we've got 3.5 measured from the emitter, 3.52 to the collector, and 0.7 to the emitter. And what I will be left with is the difference. I didn't pre-calculate this, so give me 1 second. 3.52 minus 0.7 equals 2.82 volts. That's the difference between the base and the collector. 2.82 volts. So again, if I were drawing a load line for this and saying up here was saturation and down here was cutoff, right, and the operation of this transistor is in between the two, this being VCE, this being IC, the Q point should be in the center, but looking at this, it's obviously running a bit closer to saturation. So the Q is probably here, which means when we start moving the base up and down, it's going to hit saturation long before it hits cutoff.